Hello everyone, today we're talking about determinants as a measure of area or volume, material from 3.3. So at this point, we've seen the determinant. It's this number that we can assign to an n by n square matrix. And it has nice properties. It detects whether the matrix is invertible, but it's maybe a little mysterious where it comes from. And so the goal today is to give a geometric description of this thing called the determinant of A. And I like to do this whenever I can. I think there's a lot of nice geometry underlying these ideas in linear algebra. And in fact, the determinant, I would say, the reason it was invented and then the kind of why it's so important is that it provides a way to measure area and higher dimensional volumes that we'll see in a second. So I think I'll just start with a fact. Suppose P is a parallelogram, let's say, determined by vectors, say v1 and v2 in the plane R2. So I'll explain in a second what I mean by determined by. But let me just tell you that the area of P, then the area of P is given by well, the determinant of a certain matrix. What I do is I take v1 in the first column, v2 in the second column. It's a little 2 by 2 matrix. That might be negative, so we take the absolute value. And let me do this with an example. So e.g., if v1 is, let's say, 2 minus 1, v2 is 4, 2. Try to draw this thing in the plane. So let's see. 1, 2, 3, 4. 1, 2, 1, 2. So 2 minus 1 is going to be something here. This is like v1. And then v2 is 4, 2. So it's something like this. And when I say the parallelogram defined by these two vectors, right, this is something we've seen before. For instance, if I take the sum of these two vectors, right, I get something over here, and that's the parallelogram that I mean. So this is P here. Okay. So what's the area of P? It's going to be area of P equals the determinant of 2 minus 1, 4, 2. So what is that, right? It's just going to be 4 minus 4. In this case, it's 8. Okay. So that's that's the tool. That's a nice little fact. Now, it turns out that this is actually, this generalizes to higher dimensions. So I'll say a little bit why that works in a second, but in higher dimensions, what's pretty cool is that this generalizes. So for instance, I'll just say it this way, fact, now let's suppose P is what's called parallelepiped. Is it O or A? I never remember there, but it's the parallelepiped determined by 3 vectors, determined by v1, v2, v3, and now we're in R3. And so I'll try to draw a picture of this in a second and probably fail, but the fact that is then the volume of, I'll make this a fancy P. The volume of this fancy P is given by the same thing, basically, right? You take the determinant of this 3 by 3 matrix now you have, put that into a matrix, right? You got a 3 by 3 matrix, you can take the determinant and you take the absolute value. So what do I mean by a parallelepiped, right? So let's see if I can draw this. So here's V1, let's say. I'm not going to draw the axes just to make my life easier. Maybe this is V2, and let's say this is V3. Okay, so just like the parallelogram was kind of a, shifted rectangle or square, this is going to be kind of a box-like thing. So, it's going to be something like this. Okay, so that's the idea, is that you get, of course this is supposed to be 3-dimensional. Okay, so that's not too bad, right? This is going to be P. So, you think about this as sitting in the 3-dimensional space, and it defines this cube-like object. And it has volume, right? It's a 3-dimensional object, and its volume is given by the determinant of this matrix. And what's kind of cool then is you can keep going, right? So for n bigger than or equal to 4, the same statement holds. In fact, this is one way to define volume for higher dimensions. In fact, can use this to define what we mean by higher dimensional volume. Right? We know how to take determinants of 4x4s and 5x5s, etc. And so that will be our definition of actually volume in that higher dimension. Actually, let me just give you guys a real quick example of this that we'll come back to in a second. Suppose my parallelepiped was just actually a sort of rectangular cube. So if you had something like this, if this was like 2, 0, 0, and then let's say this is 0, 3, 0, and then I had something like 0, 0, 1 here, well, that would actually just be a, what is this called, a rectangular cube or something like that, right? And so what's the volume of this thing? Well, right, this is just, width times height times depth. So this volume of this thing is equal to just, well, the determinant of, right, let me reorder these things how I like so I can easily take the determinant. Notice that this is actually just a diagonal matrix, so this is actually equal to 6, and of course that's the dimensions of this box, okay? So let me just show you kind of why this works for the plane at least. So say, why does this work? Let's say in the plane. Well, again, just what I said, so note that if, let's say v1 is just x0 and v2 is just 0y, then what I'm looking at is just, this is just x0 and this is 0y. And what's my parallelogram? It's just this rectangle. So the area we know is just equal to x times y, which in fact equals the determinant of, well, notice actually, okay, so this is 0, if I put the columns in this order, notice that if I take absolute values, this is also equal to the determinant of, if I put 0y x0 here, up to absolute value, this is the same thing. And notice that the sign change here, right, the reason I get a different sign, this is of course -1, this is minus xy. The sign is determined by which order I put those vectors in. And the reason it picks up that minus sign is that we have this convention, right, that this is always the positive. So you've probably seen this before, that in our coordinate system, we always assume that this is the positive direction. So if I put x0 first, right, in my column, then I get xy, what I want. If I put 0y first, well, that's kind of going the wrong direction. So what I get is a -1. But that's okay because we're talking about area, which is a positive or at least non-negative thing anyway. And now the next thing I want to show, so what I'm saying here is that the theorem, the fact holds if you just gave me a kind of simple rectangle. But now if you shift, so now consider, so let's say this was V1, that was V1, this was V2. Now consider a picture like this where I still have V1 here, which was x0. But now I'm going to take a little bit, I'm going to take V2 was here, I'm going to shift it by taking a multiple of V1. So this is V2 plus CV1, right? I've replaced now V2 with a multiple of V1, right? Because I took a little bit of V1, I added it to V2 to get this new vector. And now what I got is this, parallelogram now, right? And we know now that the area of this thing, just from high school geometry, is still equal to, right, base times height. So the area of a parallelogram is just base times height. This is still xy. But notice that what we know from our previous discussion is that this is the same as the determinant I get by taking, right, this new, so what is this going to be? This is going to be V2, which was 0y plus c times x0. So this is just cxy, okay? And so now what I have is, this is, what is it, x0 in the first, and then cxy in the second. And now look at this determinant, right? I've only changed that entry there, and when I take that determinant, it's just still xy. Okay, so what you see now is there's a little bit more of an argument to make, but the next thing you can do is assume that your parallelogram is actually sitting on this x-axis. But at least in this case, you can actually see the kind of all the mechanics at work. And in the end, you get this nice kind of area interpretation of the determinant. So I think I'll end there. We'll see you next time.